Hey everyone, and welcome. Today we're tackling a pretty tricky Leetcode hard problem, minimum difference in sums after removal of elements. It sounds complicated, but don't worry, we're going to break it down step by step into a really clear and understandable solution. Let's get started. Okay, so here's the core idea. We're given one big list of numbers. The length of this list is always a multiple of 3. Let's say 3n. Our job is to remove exactly n numbers from it. The two n numbers that are left get split into two equal parts. The first n numbers form the first part, and the next n numbers form the second part. The goal is to make the sum of the first part, minus the sum of the second part, as small as it can possibly be. Let's walk through a simple example. Imagine our list of numbers is just 3, 1, and 2. In this case, n is 1. So we have to remove one element, and the remaining 2 will form our two parts. What happens if we remove the first number, the 3? We're left with 1 and 2. The first part is just 1, the second part is 2. The difference is 1 minus 2, which is negative 1. Okay, what if we remove the middle number, the 1? We're left with 3 and 2. The difference is 3 minus 2, which is 1. You can see how this works. After checking all the options, the smallest difference we found was negative 1. So how do we approach this systematically? To get the smallest possible result from a subtraction, you want the first number to be as small as you can get it, and the second number to be as large as you can get it. Here that means we need to choose elements to make the first sum tiny and the second sum huge. The really tricky part is that we don't know where the first part ends and the second part begins. This dividing line could be in many different places. The most efficient way to solve this is with a two-pass approach using priority queues, which are also known as heaps. First, we'll go from left to right across the array. In this pass, we'll figure out the minimum possible sum for the first part, considering every possible endpoint. Then, we'll do a second pass, this time from right to left, to find the maximum possible sum for the second part, for every possible start point. Once we have these pre-calculated values, we can just compare them to find our answer. Okay, let's dive into that first pass. As we move from left to right, we want to keep track of the sum of the n smallest numbers we've seen so far. Now it sounds a little backwards, but the best tool for this is a max heap. A max heap always puts the largest item at the top. So we can keep adding numbers to it, and if it ever gets bigger than size n, we just remove the largest element. This cleverly leaves us with only the n smallest numbers we've encountered. We'll calculate the sum and store it for each position. Now for the second pass, going from right to left. This time our goal is the opposite. We want the sum of the n largest elements in the rest of the array. For this job, a min heap is perfect. A min heap keeps the smallest item at the top. We'll add numbers to our min heap, and if it gets too big, we'll just remove the smallest one. This ensures our heap always holds the n largest numbers. Again, we'll calculate this sum for each possible starting position of the second part. Alright, we've done the hard work. We have two arrays of pre-calculated sums. One holds the smallest possible sums for the first part. The other holds the largest possible sums for the second part. Now we just loop through all the valid places where the array could be split. For each split point, we grab the corresponding minimum prefix sum and subtract the corresponding maximum suffix sum. We keep track of the smallest difference we find, and that's our final answer. Here is the complete Python code that implements the logic we just discussed. It might look a little dense at first, but you can clearly see the three main parts. The first loop for the prefix sums, the second loop for the suffix sums, and the final loop to combine them and find the minimum difference. Let's zoom in. In the first part, notice how we push the negative of the number into the heap. This is a classic Python trick to make a min heap behave like a max heap. When we pop, we get the largest number, well, the most negative number, which corresponds to the largest original number, and we add it back to our sum to cancel it out. The second part is more straightforward. We use a normal min heap and just subtract the smallest element when the heap gets too full. It's two sides of the same coin. So what's the performance like? The time complexity is big O of n log n. The n part comes from us having to iterate through the array. The log n part comes from the heap operations. Adding or removing an element from a heap of size n takes log n time. For space, the complexity is big O of n. This is because our heaps can grow up to size n, and we also need arrays of a similar size to store our pre-calculated prefix and suffix sums. Let's recap the main points. First, we took a complex goal and broke it down into simpler parts, making one sum small and another large. Second, we saw how powerful priority queues are for keeping track of a running collection of smallest or largest items. And finally, this problem is a fantastic example of pre-computation. By calculating all the possible prefix and suffix sums first, the final step of finding the answer became simple and fast. And that's a wrap. I hope this breakdown made the solution clear and the logic behind it easy to follow. If this was helpful, please hit that like button, subscribe for more Leetcode explanations, and feel free to ask any questions in the comments. If you're feeling extra generous, you can support the channel through the Boba Fund. Thanks for watching. Keep up the great work, and I'll see you in the next one.